Okay, welcome to lecture 10. This lecture is going to take part in two sub-lectures. We're going to first continue instruction set architectures that we started yesterday and finish it. There's a lot to cover in instruction set architectures, actually. It's a fascinating topic, the hardware-software interface. And we will revisit part of it later, but we're not going to be able to cover a lot of trade-offs related to instruction set architecture since it's an introduction course. So I'm going to give you some pointers to some other lectures that you can potentially study if you're really interested in learning further about instruction set architectures. And there's a lot of historical information about this also. And then we will, in lecture 10B, we will give a quick overview of assembly programming. Let's see how much time will be left for that. Just as a reminder, you have some assignments to do until April 5th, as you know, and this is what we were covering. Yesterday, we covered the von Neumann model and talked about instruction set architectures and an example of a von Neumann machine, LC3. Today, we will essentially continue that and go into a bit more detail and talk about assembly and programming as well. And then next week, we're going to jump into microarchitecture in more detail. Okay, these are some readings that I would recommend you take a look at to get further information or to reinforce what we learn in class. Okay, recall this slide. We basically said this is what we were going to cover, and we covered a good chunk of this, but we're going to continue covering essentially this today, looking into the software hardware interface as well as the microarchitecture. And recall yesterday we talked about 5 components of the von Neumann model, and we're going to continue looking at those components in some detail. And recall that we also talked about 2 key properties of the von Neumann execution model. Remember that we need an execution model to process instructions in order to build a computer. Neumann was one of the first to propose one of those execution models, and it's a very fundamental execution model that he and his co-authors have proposed that has been extremely successful. As I said, all major instruction set architectures today are based on the von Neumann model. And the 2 key properties are the stored program computer. Instructions are stored in memory together with data, and sequential instruction processing. Essentially, instructions are processed in sequential order. And this helps the programmer to write programs and expect a sequential execution from the machine. And recall that we also talked about programmable visible architectural state. And this is also very critical for the von Neumann model. This is what gets exposed to the programmer, memory, program counter, and registers. These are the major chunks. Of course, there are other things that may be exposed depending on the ISA. Essentially, anything that gets exposed to the programmer from the underlying machine is the programmer visible state. If some register inside the machine is not visible to the programmer, then it's not programmer visible clearly, and the machine can do anything it wants with it. But whenever the machine is writing to these registers, memory, and program counter that's visible to the programmer, it should be very careful. It should not do something that is not dictated or expected by the programmer. Okay, we will see more of that later on. And recall that we covered the basic microarchitecture of a von Neumann machine, LC3, which looks like this. We went through actually each of these components yesterday. It looks busy right now, but we went through each of them one by one. And we're going to go through this machine again, and maybe go into a little bit more detail into these components as well in this lecture. Okay, and also recall the instruction processing cycle. Remember that we said instruction processing happens in phases, and there are 6 phases: fetch, decode, evaluate address, fetch operands, execute, store result. You do all of this for one instruction, and then you fetch the next instruction. And then you do all of this for the next instruction, and then you fetch the next instruction. Basically, you keep doing this. And remember that this has nothing to do with clock cycles. This process, this entire instruction processing cycle can take multiple machine clock cycles. So those are different. Or it can take a single machine clock cycle. We will talk about that next week, actually, whether it takes single cycle, multiple cycles, what are the trade-offs associated with it, etc. And we also said that not all instructions have all the phases. For example, an add operation in LC3B or MIPS doesn't have the evaluate address phase because it has no memory address to evaluate, right? Okay, now this is where we stopped yesterday, LC3 and MIPS instruction set architectures. I gave you a very quick overview to jog your memory. We're going to continue our exploration of these 2 instruction set architectures. And while doing so, I'm going to hopefully give you some fundamentals about instruction set architectures, as well as we will briefly talk about some trade-offs, but we will not go into a lot of detail in trade-offs. So we defined instruction set yesterday. Basically, it's the vocabulary of the computer, right? As we discussed, it's a set of instructions that is exposed to the programmer that could be used to program the computer. And the instruction set defines each instruction essentially It defines the opcodes and the format of the instruction, data types that are used by the computer or interpreted by the computer, and the addressing mode, how you calculate addresses for different instructions. And remember, we discussed add operation and load register operation. Those are our first examples. Now we're going to go into a little bit more detail. So add looked like this, for example, in LC3, and load register looked like this, basically. And remember that add uses the register mode, addressing mode, which means that you take a source register 1, add it to source register 2, and write the result into destination register. In this case, source register 1 is register 1, source register 2 is register 2, and destination register is register 0. And so opcode is 1 in LC3. So this is the register addressing mode, basically. LDR, load register, uses the base plus offset addressing mode, which is you take the value inside the base register 0, in this case, add to it an offset 4, and go to memory in that address, take the data in that location in memory, and put it into the destination register 3. If your opcode is 6, of course, you do this, basically. This is, again, a kind of review, but important review, because we're going to continue with similar instructions today. So essentially, another view of instruction set architecture is that it is the interface between what the software commands and what the hardware carries out. So you look at the software parts, the bluish parts over here, and the hardware parts that are the greenish parts over here. In the middle sits a yellow portion, which is the hardware software interface, or ISA, essentially. And the ISA specifies everything that the programmer or the compiler writer, whatever software provider, essentially, needs to know so that they can execute operations inside the hardware that's provided by the machine. So this essentially consists of the memory organization, as we discussed. Remember, we talked about address space, addressability, whether you have word addressable, byte addressable, whether your memory is byte addressable or word addressable, minimum granularity. We discussed all of this yesterday, so I'm not going to go into that. And you remember the numbers also, hopefully. Address space of MIPS is, for example, 2 to the 32. Addressability of MIPS is 32 bits. But actually, MIPS is byte addressable also, right? This needs some change, actually. Okay, MIPS is really byte addressable over here. The register set we also talked about, that is also part of the ISA, because this is exposed to the programmer. Remember, this is temporary storage that the programmer is supposed to manipulate so that they don't need to go to memory, right? In LC3, you have 8 registers, and MIPS, you have 32 registers. And the instruction set is also what we started talking about, opcodes, data types, and addressing modes. And we're going to talk about this a little bit more. Let me correct this slide very quickly, because addressability of MIPS is really 8 bits, right? It's a byte addressable machine. So there's a mistake on the slide. Okay, so let's move on. Let's talk about the instructions now a little bit more. So instruction requires opcodes, right? And you may have a large set of opcodes or small set of opcodes. The computer may expose you a very large set, a very small set, or different levels of complexity of opcodes. The instruction may be very complex, very simple. We're going to talk about the trade-offs at the end very briefly. I'm not going to go into the trade-offs a lot today, but think about some instructions. For example, an old architecture, HP precision architecture, which is not used as much today, had an instruction that would do this: multiply and accumulate. This was not common in many instruction sets at the time, but these folks said, oh, multiply and accumulate is very good for matrix multiplication. And we actually want to add this instruction that can do multiply and accumulate inside our ISA. Now, that was actually a good idea, perhaps, if you think about machine learning today. Machine learning is full of matrix multiplication operations and accumulation, of course. Matrix multiplication requires both multiplication and addition operations. As a result, these multiply and accumulate instructions can come in very useful for workloads that demand them. So you can see that you can add an instruction that's slightly more complex. It's more complex than multiply, more complex than add. It basically combines them, and you can express your your matrix multiplication in much fewer instructions if you have an instruction that looks like this. Or you could have a direct matrix multiply instruction, right? That basically takes one array or one matrix and another matrix and does the multiplication, and the result is supposed to be stored somewhere. And you define that as a single instruction. Now you're raising the abstraction level a lot if you actually do it that way. It's a complex instruction, clearly. It's doing a whole matrix multiplication in one instruction. Internally in hardware, how do you design it? That's a different question, of course. But clearly, what is exposed to the software could be a matrix multiplication, right? And that basically says that the level of the instruction set architecture is very close to the high-level language. So high-level language, or programmers thinking, is about matrix multiplication. And the instruction set is very close to that because you can express matrix multiplication with a single instruction. So in many cases, you don't have that today in many architectures, but it's possible to think of it that way. So these are trade-offs related to the architecture. In the architectures we're going to examine, instruction set architectures, we're going to examine MIPS and LC3. They don't have complicated operations. We will see some complicated operations, but they're nowhere to the level of specifying a matrix multiplication, for example, or even floating multiply and add doesn't exist in these ISAs that you're going to program in. But keep in mind that there are other instruction set architectures that are much more complex, and HPPA is one of the simpler ones that have some complex operations. x86 ISA, for example, and this is true for many ISAs today, but x86 was the first one to introduce multimedia extensions. These are actually, we will cover these in more detail, but these are actually the single instructions that can operate on multiple pieces of data. You can operate on 8 pieces of data at the same time concurrently, for example. And this was helpful in image processing applications. Later, they basically introduced the streaming SIMD extension and later advanced vector extensions, which were all evolved from MMX. Later, when we talk about single instruction multiple data architectures, we will see that these are actually single examples of single instruction multiple data operations. And these are more sophisticated than what we will cover today and what we will see in your labs. But keep in mind that you could actually express these things. And GPUs are another example, as we will see later on. One of the most complicated instruction set architectures that are very close to the high-level language, VAX ISA, virtual address extensions, that's the name, basically. It had an opcode instruction to save all information of one program to memory before switching to another program. It was called save context, for example. And this is actually interesting, right? You could basically save all of your architectural register to memory and some other some other registers as well, like program counter, etc. So this is a complicated operation, right? The decision, they made the decision saying that, oh, this instruction is reasonably frequently executed and we want to optimize it in hardware. And we want to minimize the code. If you express this with a single instruction, this operation with a single instruction, your code will be smaller. You, of course, write code that loads and stores and calculates the address, etc., and does this in a loop, for example, saving every single register, but it takes a lot of code and effort. So clearly, there are a lot of trade-offs involved in this, designing the instructions of an ISA, which we're not going to go into, and they affect both the hardware complexity and the software complexity. So remember, if your instructions are closer to the high-level language, then maybe it's easier to compile the high-level language into your instructions because you have a matrix multiplication. The compiler just says do matrix multiply instruction, right? But if your hardware, if your ISA is far away from the high-level language, which means that you have very basic operations in your ISA, like add, and, not, multiply. Even multiply can be considered complex by some measures, right? If you have very basic operations, nothing like matrix multiply, then you have to express that matrix multiplication as a function of many of these additions, multiplications, shifts, etc., right? And loads and stores from memory as well. So now your software becomes more complex with simple instructions, potentially, but your hardware becomes simple. So in general, if you have very simple instructions, very few instructions, hardware is simpler, software is more complex. And if you have complicated instructions, then if you're complicated instructions and a lot of instructions, let's say, then your software is simpler and hardware is complex. That's, of course, general. There could be other trade-offs that may be involved depending on the type of instructions that you introduce. Okay, so in LC3 and MIPS, as we said, we're not going to see these complicated instructions. We're going to see simple instructions. And we're going to see, start with the simplest ones in this lecture. We're going to cover 3 types of opcodes: operate, data movement, and control. And I already mentioned each of these, but I'm going to go into more detail later on each of these. So let's take a look at the opcodes in LC3. Basically, in LC3, you have 16 opcodes, as you can see over here, because you have only 4 bits by the opcode in the instruction format. That was a decision made by the instruction set architects, basically. And you can see that this is one version of the LC3 ISA, and one opcode is reserved. So in case somebody wants to add another instruction in the future, you can use that. Okay. And this is LC3B. This is the byte addressable version. This is to show you that ISAs, instruction set architectures, also evolve over time. Even educational instruction sets evolve over time. You can see that there are some differences. I will highlight the differences. It has a jump subroutine, which didn't exist over there in a different way, actually. JSRR it has. It has an XOR also. It eliminates the not, for example, over here. So it doesn't. This doesn't have a not, for example, and as a result, it has basically two unused operations. Basically, it got rid of a JSR and one of them actually. JSR and JSR are not separate instructions anymore. They're basically combined in the next ISA. Basically, ISA designers can also figure out that they made a mistake and they can change the ISA. But think about the implications on software. If you change the ISA, the software that already was written, that was compiled into the previous ISA, now may not work in the future ISA that has changed. So you need to be very careful when you're actually changing the instruction set architecture. If you don't preserve backward compatibility. Now, what does that mean? Basically, software that was compiled to an older version of the ISA should be compatible with the newer version of the ISA. So basically, what I assumed based on the older version of the ISA and wrote software in should execute seamlessly and correctly in the newer version of the ISA also. If that is not true, then you did not preserve backward compatibility when you actually evolved your ISA into the future. And as a result, you may, some code that is out there that was written for the previous version of your instruction set architecture maybe get broken, right? It just doesn't get executed. It just cannot execute, right? And that's a problem, right? Clearly, you need to preserve backward compatibility. But that may not, if you don't do that, then you're basically making a trade-off, giving up, saying basically, I don't care about existing software that uses these instructions that have changed. Let those not work in the newer versions of my ISA, right? That may not be a good thing. And that is, if you have a very large software base, if you have a huge, if your ISA was popular, let's say, and x86 was very popular, for example, and it's still very popular, as you can see. If you try to completely change the ISA, even if you may be a highly influential company, you may not be able to do that. So Intel tried that, for example. Intel, at some point in late 1990s, early 2000s, there was a debate in terms of, oh, we have the x86 architecture. Can we actually change that to something completely different so that we can get rid of some of the baggage in the x86 architecture? Because x86 architecture is really, really complex, much, much more complicated than MIPS that you're going to see. And they basically said, can we actually get rid of this complexity and switch completely to a different architecture, which was called IA64 at the same time. So it was also 64 bits. And Intel actually did put a lot of effort into trying to design that IA64 architecture, instruction set architecture. And they did, but they were not able to get a huge portion of the market, software market, to use the IA64 architecture. Why? Because everybody was writing code. Everybody had a lot of code that was written in x86, and people did not really want to go through the effort of recompiling or rechanging the code such that it executed on IA64. Okay, so this is one example. So basically, there's a huge software stack that gets written, assuming the hardware-software interface, right? Because programmers compile down to these ones and zeros that are specified by the ISA manual. And if you change the manual and say, okay, what you thought was an add is not an add anymore. It's a return instruction just because I needed to make that change, then you're breaking the old code, and that's a problem, basically. So that's why it's very hard to change the instruction set architectures in a way that is really, really significant. Basically, you need to come up with a software ecosystem that can support it also, and that's also very difficult, even for the larger companies. Okay, I had to talk about this because it's really important in practical life. Okay, let me go into the opcodes or instruction types in MIPS. We've seen some of those. We're going to see more. So MIPS actually is also very simple. As I said, this is an R-type instruction. It's an I-type instruction. It's a J-type instruction. And we've seen all of those, actually. We're going to see them in a little bit more detail. And as I said, this is the opcode. What differentiates them is the opcode. R-types are always 0 opcode, but then there's a funct field that basically specifies what kind of operation should be done, which means that this is another part of the opcode, if you will. Okay, so let's take a look at that funct. So this funct is really function, essentially. That's why funct means. That's what funct means. They couldn't write function for whatever reason in MIPS. But basically, this is a 6-bit field. You can see that. And it basically defines what your operating instructions could be. And it's not just operating instructions, actually, interestingly. It's just R-type. That's why this is called R-type. And you can see there's some shift instructions, jump instructions, even move instructions, break, system call, etc., divide, etc. So basically, func defines the operation in general. It's really an extended opcode, if you will. So this is a trick that ISA designers, instructions and architecture designers play so that they can have a bigger opcode space. So if you were restricted to, for example, just these 6 bits, you could have only 64 operations. But these folks played the trick saying that, oh, if my opcode is 0, I'm going to have some more opcode, 64 more bits. Sorry, 6 more bits, essentially. That gives you 64 more instructions, right? You could do the same trick for opcode 1, opcode 2, opcode 3, etc. And now your opcodes become a lot. And that's one of the ways in which x86 architecture has more than 1,000 of instructions, let's say. That's a lot, actually. But yes, that's how you play these tricks in the encoding, so that you look at some other part of the instruction encoding to determine what your operation should be, right? Okay, so these are interesting tricks, which we will not necessarily go into, but I want to attract your attention to. You can see that not all of the funct fields are used in this MIPS architecture. You can see that even though you could specify 64 of them, they don't specify every single one of them in this case. And you can find the complete instructions in appendix. Okay, that was opcodes and instructions. We're going to get back to this later at the end of this lecture, maybe, depending on how much time we have. And ISA also supports data types. So data type is very similar to data types you have in programming languages, right? Integer, floating points, or you could have an array, or you could have a linked list as a data type, potentially. You could have a tree as a data type. And all of these data types can potentially be supported inside the hardware interface as well. But of course, there needs to be a decision to be made by the instruction set architecture designers. What are the things that we support? And again, similar trade-offs exist over here. For example, LC3 is very simple. It supports only 2's complement integers in terms of the arithmetic data types. 2's complement will become more clear in this lecture, but we didn't cover it, but you can actually read it in your books. It's essentially one way of representing signed numbers such that addition and multiplication, addition and subtraction become easier. And 2's complement is a particular way of representing integers such that the integer and its negated value, when you add them together, you get a 0. And the way you do it is basically the negated value of a value is taken by complementing, bitwise complementing the value and adding 1 to it. We will see this later on when we talk about subtraction and addition. But essentially, 2's complement is one way of representing signed integers, right? Okay, I already said this actually, but we're going to see it more. Essentially, negative of a 2's complement binary value x, if you have a value x, the negative of it is computed by doing bitwise not of x plus adding 1 to it. And if you do this, you can convince yourself that x plus minus x is equal to 0 in the representation that's given. Okay, MIPS supports, in addition, 2's complement integers, unsigned integers also. It doesn't. It also can. You can also treat some instructions treat integers as unsigned. They don't have to be signed. Basically, they go from 0 to some maximum value as opposed to minus some maximum value to plus some maximum value. And it also supports a format called floating point, which can enable the computer to process essentially operations with different levels of precision, right? 1.5678, for example, right? You could express that very easily with a floating point format, and it's very difficult to express as using integers. You have to do a lot of work to actually convert the integer to that value with a lot of instructions. So basically, the data types that you support make it easier or harder to implement high-level data types inside the architecture. So if you're using floating point operations, for example, in your matrix multiplication, if your instruction set architecture doesn't support floating point operations, good luck. You'll need to construct the floating point operations using, for example, these 2's complement integers in LC3. You need to figure out what is the fraction, what is the significant part of the operation, etc., and do all of that in software using very simple instructions. Whereas if you have a floating point operation, that's easier. Right? Again, there are many trade-offs involved. What data types should be supported and what should not be. Again, that's the decision of the instruction set architect. But again, the decisions that are made over here are very much affect the software complexity and the hardware complexity as well. Clearly, if you support floating point, hardware becomes more complex. If you support, for example, a matrix and a matrix multiplication, that's essentially a data type, right? Matrix itself is a data type.
then you need to basically define it, and clearly hardware becomes more complex. But then the software becomes easier potentially, because the software doesn't need to go through very simple operations like add, not, shift, multiply, etc. If you have multiply, to actually do the matrix multiplication. Okay, so hopefully this is clear. And as I said, data type trade-offs. What is the benefit of having more or high-level data types in the ISA? What is the disadvantage? I think I've already given you the high level. Think compiler, programmer versus the microarchitect, essentially. If you have data types that are closer to the high-level language, like matrices, vectors, and floating point data, for example, then you make it easier for the compiler and the programmer, but make it harder for the microarchitect. And again, this is also another example of the concept of semantic gaps. Semantic gap. Data types are coupled tightly to the semantic level or complexity of instructions. How close are instructions to high-level languages? If you're close, then you make life easier for the programmer. If you're far away, you make life harder for the programmer or the compiler. Again, there's a lot of history to cover. I don't want to spend a lot of time on this one, but there was a lot of debate in computer architecture in 1980s, 1970s, all the way into 1990s. Early risk-reduced instruction set computing architectures were proposed to actually increase the semantic gap, basically make the hardware as simple as possible, but put a lot of work on the compiler, so that you have very simple instructions, but the hardware will be simple. And then there was another philosophy, which was proposed by Intel: make the hardware complex, but make the life of the programmer easier. For example, early machines had only integer data type. They didn't even have floating point. And then later they figured out that this was a bad idea, because a lot of programmers need the floating point. And if you actually try to emulate floating point using integer, it takes a lot of additional instructions. Intel 432 was the opposite, basically. It had the object data type. It had actually really interesting ideas, which I'm not going to go into right now. If you're interested, you can study it. And VAX ISA had complex types. For example, it had a doubly linked list. This is not imaginable in a simple machine, for example, like MIPS. Doubly linked list, essentially, it was directly exposed to the programmer, and the programmer can basically say, I want to add a node to this doubly linked list. And the hardware would take care of adding the node internally to the doubly linked list. You can see that this is very clear to the very close to the higher level language that can support doubly linked lists. Okay, clearly there's a lot more to cover here, but we don't have time. But hopefully this is interesting to you. Let me give you a funny example. And this is a data type that was used and proposed by people. This is called binary coded decimal, BCD. Maybe some of you have heard of it. Has anyone heard of this binary coded decimal? Yeah, maybe, I don't know. Nobody is raising hands, so maybe not. This is maybe old. Essentially, each decimal digit is encoded with a fixed number of bits. And people thought that this was a good idea for displaying numbers, for example. Let me give you an example of this. So imagine that you're encoding time. It's 37 past 10, and you're 49 seconds into the 37th minute. This is one way of encoding it. Look at this picture over here, right? And this is binary, right? The top digit, the bottom digit can take a value anywhere between 0 to 9 over here. And you basically have a binary encoding here, 4 bits, specifying 1, 2, 4, 8. In this case, none of the bits is set because it's 0. And then the top bit can be, in this particular case, it can be 1 or 2, I guess, right? In this case, it's 1. So you set this to 1. And if you look over here, 7 is encoded as 1 plus 2 plus 4. So you have these values as set. And 3 is encoded as 1 plus 2, as you can see over here. And then here, 9 is encoded as 1 plus 8. And 4 is encoded like this. So now you have a clock that looks like this. And actually, these things exist. You can buy them if you're interested. So you can represent 12, 15, and 45 seconds into the 15th minute using this binary coded decimal clock. But you can clearly see that this data type is not very friendly to humans, let's say. It may be friendly to computers, but it may not be very friendly to humans. Of course, you could actually get better at it to read your clock this way and have fun if you're a geek, for example. But I would prefer my clock this way much more easily. This is a bit harder, I think. But clearly, these are two different data types that are used in a real clock over here. And I think this hopefully conveys the concept. Do you make life easier for the programmer, or do you make life harder for the user? Let's say, in this case, user is a programmer, if you will. And you can see that this is a bit easier. for the user over here because it's much more high level, whereas this is much more lower level representation that may be easier for the computer itself, right? Whereas this is much more higher level representation that's much easier for the program, for the user like me, at least. Okay, so hopefully this clarifies the concept of the semantic gap. So the semantic gap between my level of thinking and this clock is much lower, whereas the semantic gap between my level of thinking and this particular binary coded decimal clock is much farther away. I have to do a lot of processing to really understand what this clock on the right is telling me, as opposed to what this clock on the left is telling me. Because the instructions, let's say, that is used in this clock may have been actually very simple, right? Okay, that was data types. And ISA also specifies addressing modes. And addressing mode is a mechanism for specifying where an operand is located. We discussed this yesterday also. And there may be many, many addressing modes. Okay, so in LC3, for example, there are 5 addressing modes. We're going to see them. Immediate or literal is constant. And in this case, the operand is in some bits of the instruction, as we saw yesterday a little bit. Register addressing mode, we just saw it actually. The operand is in one of R0 to R7 registers. And 3 memory addressing modes. One is PC relative, one is indirect, and the other is base offset. So we've seen base offset yesterday. We're going to see it again, but we're going to also see the PC relative and indirect. And essentially, these addressing modes enable, again, different high-level structures to be mapped into the hardware in a better way. So for example, if you're doing pointer chasing, pointer access, linked list accesses, indirect addressing mode is going to be very useful because it's going to fetch a location from memory and use it as an address, and then take that address and again use as an address so that you can access memory again with that address and then get the data. So basically, you do 2 memory accesses to get the data you want. The first one is to do the memory access to get the address from that location, and then the second one is to do the memory access with that address so that you get the data. And we'll see this in more detail, but this can enable pointer-based access is much better. So MIPS has pseudo-direct addressing for jump and link, as we will see, as we saw actually earlier, additionally, but does not have indirect addressing. So MIPS actually has all of these addressing modes as well, but in addition, it has pseudo-direct, but it doesn't have this indirect because they thought you could actually use more instructions to be able to do this. Okay, so we're going to see more examples of this, but let's talk about the high-level trade-offs. This is another example of the programmer microarchitect trade-off, basically. You can have more addressing modes. That makes the life of programmer easier, but the life of microarchitect harder. Basically, it enables a better mapping of high-level programming constructs to hardware, assuming you pick the right addressing modes, of course, right? So some accesses are better expressed with a different mode because you can have reduced number of instructions and code size, just like we did with the data types. So for example, array indexing is done well with base plus offset, as we discussed yesterday, register plus offset addressing. Pointer-based accesses can be done more easily with the indirect accessing mode. Sparse matrix accesses might be supported with some other addressing mode that can enable you to find the non-zero elements, for example, in a matrix. Today, this is actually very common in machine learning workloads that operate on sparse data. And I think people may think about new ways of addressing memory so that you can actually get the non-zero values very quickly. Again, if you didn't understand that, don't worry. But basically, the key idea is, can you map the high-level memory access patterns of an application, of a program, well into the hardware-software interface? Of course, if you have more addressing modes, there's more work for the compiler and more work for the microarchitects. But it could be easier work for the compiler also, depending on what the addressing modes are and how they're related to the data types and memory access patterns. Okay, there are many, many more trade-offs in ISA design, which we're not going to cover. Execution model, we're going to get back actually. Even sequencing model and processing style, we assume von Neumann. But later, we're going to see data flow computers, for example. Even that can be questioned and changed. And we're going to talk about the trade-offs. Instruction lengths, formats, types, complexity versus simplicity, data types, number of registers, addressing mode types and count, memory organization, memory access restrictions and permissions, whether you have support for multiple instructions to execute in parallel, whether an instruction encodes multiple operations at the same time concurrently. Those are all really interesting questions, which we're not going to tackle in this particular lecture, but later we actually will talk about some execution paradigms that use different types of ISAs for this purpose. Now that I've introduced the high-level trade-offs, now let's go into operate instructions. We're going to study some more instructions in the MIPS and LC3 ISAs and how they operate so that you get more familiar with them and see how they execute in a simple microarchitecture as well. So operate instructions, I think we've introduced them multiple times by now. In LC3, there are 3 operate instructions. Not is a unary operation, which means that it has a one source operand. It executes bitwise not, as expected, on a 16-bit value, because the word length, remember, in LC3 is 16 bits. Add and AND are binary operations. They have 2 source operands. And as we discussed, add operates on 2's complement numbers. And AND is bitwise operation on source register 1 and source register 2, essentially. In MIPS, there are many more, as you have seen in the funct field earlier. Most of our type instructions are actually encode binary operations, add, AND, NOR, XOR, for example. And there are also I-type versions, meaning they have one immediate operand. So in addition to a register, so they basically do register plus immediate operation, as opposed to register plus register. So basically, instead of having 2 registers as source operands, they have 1 register as source operand and 1 immediate that comes from the instruction encoding as an operand. So let's take a look at these operations a little bit. And they also, of course, before I move, don't forget that MIPS also have floating point operations, which you're not going to use a lot in this class, but in real life, you may actually use a lot. Essentially, these are floating point operations that are called F-type. Okay, let's take a look at not in LC3. This is the simplest operation, a unary operation. This is the assembly. Basically, you not R5 and put the value into R3. And this is the opcode, and this is the basically the bottom 6 bits are defined to be set to 1. And this is the destination register and source register. I'm going to go through these relatively quickly because we've seen many examples of this, as you've seen before. So you need to have the data path to enable not. Basically, not is enabled. The ALU control bits needs to specify a not from the decode finite state machine, if you remember the control signals. And then the ALU needs to do that operation. One of the input, it's a unary operation, so it has only one input, which is a source register. And then it basically inverts the source register and put the result into destination register. So basically, this is the representation of how this operation executes, at least in the execute stage, not all of the other stages of or phases of instruction processing cycle. This is the execute phase of the instruction processing cycle. And we're just looking at the data path components in LC3 that executes this not operation. So hopefully it's simple. There's no not in MIPS, actually, interestingly, as I didn't show, but of course you may not have seen because we didn't comprehensively cover all of the operations in MIPS. How is it implemented? Anybody wants to share any thoughts? I know it's hard to actually do it over Zoom, but okay. Let me see if anybody says something. Okay, some people say use XOR. You could potentially use XOR. I don't know how you would do XOR. Think about it, but you're getting close. Somebody said NAND. Yes, you could use NAND. I would say NOR. So MIPS, I'm not sure if MIPS has now NOR NAND, actually. I think it has NOR. So basically, you could use NOR. You could basically input. You have NOR is a 2-input operation, right? And you basically let's say you want to take the not of register 1. Both of the inputs will be register 1, right? Okay, so hopefully that's clear. I don't know if you could do it with XOR, but I didn't think about it also. So think about it if you can do it with XOR. Okay, let's move on. So operate instructions, we're already familiar with LC3's add and AND, clearly, with register mode. And these are similar to R-type instructions in MIPS. So now we're going to look at operate instructions with one literal. Immediate value, this is also called immediate, literal values. Basically, here the operand is not a register, but a field, a portion of the instruction encoding, basically, as we have also seen quickly earlier. But essentially, subtraction is another necessary operation. We're going to look at an example of subtraction as well. How is it implemented in LC3 and MIPS? Let's take a look at that. So let's take a look at operate instructions with one literal in LC3. So we're going to look at add and AND. So basically, if you want to add source register to some immediate value, this is how you would encode the instruction. This 1 specifies whether the value here, the part here, should be interpreted as an immediate or a register. If this is 1, the bottom 5 bits of the instruction add and AND should be interpreted as immediate. If it's 0, it should be interpreted as a register over here, as we have seen earlier. Okay, so op is operation, add is 0001. And if op is 0001, and this is 1, as you can see over here, what this instruction semantically specifies is source register 1, the value in source register 1 should be added to immediate 5, sign extended to 16 bits, meaning if this is a positive value, it should be positive. If it's a negative value, it should be negative. That's what sign extension means. You take a 5-bit value and extend it to 16-bit value, preserving the sign of the value. And you add those two values and store the result in destination register. So hopefully that's clear, right? And is very similar. In this case, source register 1 should be ANDed with the sign extended value of this 5-bit immediate. Okay. So basically, as opposed to having a source register 2 over here, we're replacing it with a sign extended immediate 5, right? Based on the value of this bit over here. Okay. So source register 1, clearly destination register, we already discussed that. And immediate 5 is a literal or immediate, but it's used by sign extending it to 16 bits. Okay, so this is the assembly and machine code for add with immediate. As you can see, this is another add. You basically add R4 to -2 over here and store the result in R1. Okay, and this is the machine code. And this is how it works inside the data path. Basically, part of the value, the immediate value comes from, immediate value comes from the instruction register. There's a sign extension module in hardware that sign extends to 16 bits. And then you either choose this or a source register 2. And if the bit 5 in the instruction is 1, you can see that, then you choose a sign extended value because that's what the instruction says. This is how actually the control of the mux is done, multiplexer is done. And then basically the other operand of add is always source register 1 in this case. So basically you add source register 1 plus sign extended immediate 5 from the instruction if this bit is 1 in the instruction, bit 5, and store the result into the register ID that's specified by DR, destination register, which is R1. And source register is 4 in this case. So basically you can see that you need the inputs to the decoders of the register file for source register 1 and destination register should use fields coming from the instruction as well, right? We don't show that over here, but that's how it should be. Okay, so let's take a look at the data path also for the LC path, LC3. This is an extended data path, so there's a lot more information over here actually. So if you look over here, this is the sign extension components. It comes from the instruction register. So basically it's the instruction register. Okay, I occluded that. This is the bottom 5 bits of the instruction register, sign extended, that goes into this SR2 mux. And then basically you can see that that gets input into the ALU, and ALU specifies what operation should be done based on, again, the instruction. So there's a very good question that I just saw. What if the immediate is given is greater than 2 to the 5? Essentially, you cannot represent it. You cannot do it. You cannot represent it as part of the instruction because the instruction doesn't allow you. And that's the downside. So you need to somehow put it in a register, basically. You need to somehow stuff the value in a register, construct the value somehow, put it in a memory location, load it, etc. There are many, many options. Immediate is very useful if it's smaller than what can be specified. Okay, very good question. Okay, so in MIPS, it's very similar. I'm going to go through this relatively quickly. Basically, you have I-type MIPS instructions. You have 2 register operands and an immediate. And some operate on data movement instructions also have this. Essentially, it looks like this. In a sense, it's very similar, right? So you have the opcode, and you have a 16-bit immediate right now. It's bigger immediate because your instruction format is bigger, right? 32 bits. So opcode specifies the operation. RS is a source register. RT is a destination register in some instructions, depending on the instruction. Add-I, for example, is an add with immediate and load. But RT is source register in some other instructions, which is interesting in MIPS, but that's the instruction encoding, basically. Like in store word, it's the source register. And immediate is literal or immediate. So a MIPS assembly of add immediate looks like this. It basically says add the value in register S1 to this immediate 5 that's stored in the instruction and store it into S0. That's the idea. And again, this is sign extended. You basically store a 16-bit value and sign extend to 32 bits because remember the word length in MIPS is 32 bits, right? And the machine code looks like this, and you can convince yourself that that's hopefully true. So let's take a look at subtract in LC3. So subtract doesn't exist in LC3, but you can do it using add, right? So a MIPS assembly looks like this, let's say. We're going to look at it in MIPS also. So high-level code looks like this, B plus C minus D. MIPS assembly basically translated to add and subtract, right? Assuming that registers are stored in some places. So S0, S1 correspond to B plus C. T0 is temporary. And then T0, basically you're subtracting D from T0 temporary value, which was B plus C, and then storing the result into S3. LC3, same high-level code, but unfortunately you don't have a subtract instruction in LC3, but you know the property of inverting, not inverting, basically. You know how to negate a value, right? So assume that D is stored in R3. Because of the 2's complement data type representation of assigned values, you basically take the not of R3 stored in R4 and add 1 to it using add immediate, stored in R5. Now R5 stores minus D, basically negated D value. And then you add that to B plus C, which you computed over here using the add. So this basically computes B plus C. This computes minus D in R5. And what you're doing over here is adding B plus C to minus D, storing the result into B, B in this case. So you can see the trade-off, right? Because we did not have a sub-instruction in LC3, we could still do the thing, what we wanted, but it took more instructions. So basically it took more cycles potentially, depending on how you're doing. And this is the 2's complement of R3, as you can see. So the trade-off, more instructions, but simpler control logic because you don't need to have sub in this case. Subtract immediate, MIPS assembly looks like this, basically. You have a high-level code B minus 3 over here. And you can do subtract immediate just like add immediate, very similar. But sub-I is really not necessary in MIPS in this particular case because this immediate value can also be represented as add I minus 3, right? Okay, so it's really not necessary in this case. LC3, very similar. Although, of course, the same question exists, right? One of your fellow students asked the question, what if you cannot represent the value that you're subtracting in the 5-bit immediate or 16-bit immediate in MIPS? Well, too bad. Then you need to actually put the value in a memory location or construct it into a register, as we will see later on in MIPS and LC3. You can actually construct values without going through memory and then do the operation after that. Okay, so let's talk about data movement instructions and addressing modes a little bit. We talked a lot about operate so far. Now let's go into a little bit more into data movement. So LC3 actually has 7 data movement instructions, which may sound a lot, but they're actually similar to each other. For example, LD and ST are similar, LD and STR are similar, LDI and STI are similar, and LDA actually enables you to construct values. And the format looks like this for load and store. You have the opcode always, destination register or source register specified by bits 11 through 9, and then the rest is address generation bits 8 through 0. And there are different ways of generating the address depending on the addressing mode. So there are 4 ways to interpret the bits, the address generation bits. These are called addressing modes. So PC relative mode, indirect mode, base plus offset mode, immediate mode, and we're going to look at each of them. In MIPS, there is only base plus offset and immediate modes for load and store instructions. Other instructions have the PC relative. They don't have the indirect. Ignore that. And they have one other mode. But load and store have only base plus offset and immediate modes, as we will see. Again, all ISAs have similarities to each other. That's why we are covering 2. But if you look at x86, for example, it has many, many more addressing modes. I haven't counted them, but it's at least 15 or 16 different addressing modes in x86. And in VAX, it's even more. So let's take a look at the PC relative. Actually, we've seen this before. We basically look at load and store instructions over here. And basically, the bottom 9 bits in this case are the PC offset 9. So let's take a look at what that means. Op is opcode. LD has this opcode. ST has this opcode. Destination register is the destination register in LD. The source register is the source register in ST, and they're specified by the same bits. And the address is computed like this. Basically, you take the program counter, that's the incremented program counter, as you know earlier, and then sign extend the 9-bit offset. This is the immediate value, again, literal value inside the instruction, add it to the program counter, and that's your address, basically. Now you can index locations relative to the program counter, relative to where you are in the code, basically. And you access that memory location and then put the data value in that memory location to the destination register. That's load. Store is exactly the opposite, basically. You store the address of the memory location is computed exactly the same way, PC plus sign extend offset. And then memory location at that address gets the value of the source register. So hopefully this is very simple. And let's take a look at the assembly and machine code of this. So assembly looks like this in LC3. Basically, this is the source register, this is the destination register for load, and this is the PC offset. You specify 9-bit offset over here. And clearly this is a load. And this is what the field values look like. This is what the machine code looks like. Now let's take a look at how this gets executed. Again, it's very similar. So now you have an address adder. So basically, first you need to calculate the address. So you take the program counter that's incremented. Remember, that's a part of the data path. Add to it, sign extended, 9-bit offset. And you have a 16-bit value that goes into your memory address register. And then that's the first step. Now, memory reads the location in that memory address register and then responds with the data into the MDR. And then you put the MTR into the destination register specified by the instruction, which is destination register 2 in this case. So hopefully this is very similar. Again, you can imagine the full data path, but I abstracted and put the relevant parts of the data path over here. Okay, so basically in this particular case, you may actually ask the same question that one of your fellow students asked earlier. You cannot address the entire memory, right? The memory address is only plus 255 to minus 256 locations away from the load or store instruction, right? Basically, your reach in terms of memory is very limited. It depends on where you are in the program. Now, this is not good, but in cases where this works, this is very simple. It's a very simple way of addressing. So there's a limitation though. So basically the PC relative addressing mode cannot address far away from the instruction. You're limited by the size of this offset. That size of the offset is larger in MIPS, of course, but fine. So that's why there are other addressing modes also. This is one of the other reasons why there are addressing modes exist. So the upside of this addressing mode is it's very simple. You do the calculation very quickly, right? The address calculation is really part of the instruction almost plus PC. Okay, so let's take a look at the other addressing mode. Now this is going to be a little bit more complicated, indirect addressing mode. This is load indirect and store indirect. Basically, we're going to do two memory accesses. One to get the address, and then to do another memory access to really get the data. So the first memory access is not going to be, so we're going to calculate an address, do a memory access to get the address for the next access, and then do a memory access with that address to actually get the data. So let's take a look. Basically, specification looks very similar, actually. Opcode is going to be different. So we have opcode, LDI looks like this, SDI looks like this, and then destination and source registers again. But now LDI looks like this. We calculate the address, PC plus sign extend offset, just like load. And then we do a memory access, just like load. Now we use the value that we get from that memory location as an address, and we do another memory access. So we do two memory accesses, as you can see over here. Compute the address, do a memory access, get the data value, interpret that data value as an address to another memory access, and get the data value placed into the destination register. Store is very similar, except you put the data value into that latest memory location that you address. Okay, let's take a look at the load in this case. So again, machine code, field values, those are very similar. But basically, this is how we're going to operate. We're going to first compute one address, calculate the address, PC plus sign extended 9-bit offset, and put the value into MAR. So now MAR has our address. We do a memory read. Now we get a data, and that data value is in the MDR, but then we use that and place it into the MAR again. Now we basically take that data value, put it into MAR, and then access memory again. Now the MDR has the data value that we want, and we use that to load the destination register, which is R3 in this case. So basically do two memory accesses, as you can see, because the first memory access is interpreted as a pointer to another memory location. Okay, so now the address of the operand can be anywhere in the memory. We can actually reach anywhere inside the memory, as you can see, right? Okay, base plus offset addressing mode. We've actually covered this before. LDR and STR have this, so I'm going to go through this relatively quickly. Now you're familiar with opcodes should be different clearly, and destination and source register are specified with the same bits in LDR and STR. Now memory address is calculated as the value of the base register plus a sign extended 6-bit offset from the instruction. And then we access memory using that address, and then the data gets loaded into the destination register. And store is exactly opposite. You don't load the data into the destination register, you store the data in the source register into the memory location specified by the base plus offset addressing mode. So again, very quickly, you can see what I'm doing basically. I'm going through all of the instructions like this. And this looks also very similar. But again, the address calculation logic is a little bit different, right? Now we actually, one of the sources is from one of the registers, base register, R2 in this case. We take that value, add to it a sign extended offset, 6-bit offset in this case, from the instruction, because 3 bits are used for the base register encoding. Okay, and then calculate the address, put it into the memory address register, and then wait for memory to read, and then the data comes back, and then we load it into the destination register specified by these bits in the instruction. Okay, so hopefully this is also clear. Again, here, the address of the operand can be anywhere in the memory as well, right? So there's a question. So we use LDI to load registers that are further away from our source register than plus minus 256. So not source register, further away from the program counter, further away from the instruction. Yes, you could use LDI, or you could use what I just showed you over here, which is the base register plus offset, right? So in this case, you can, well, okay, yeah, I see. Very good question. But yes, so if you're using base plus offset encoding, you're again limited to base register value plus 2 to the power of 6 over here, right? So basically, if that's the case, yes. Or you set your base register more accordingly, right? But there's no limitation in terms of which address in the memory that you can address with the base plus offset addressing mode. Okay, so basically, we've kind of constructed the LC3 data path for address calculation, right? So if this is a global bus, we actually are going to use a memory address register mux. This is how we load the memory address register, actually. And if you look over here, this is the adder that's used for address calculation. And we've seen some example address calculations here. So for example, the sign extension bits over here, this is the bottom 6 bits of the instruction. You can add that to a base register, for example, coming from here, or you can add bottom 9 bits from the instruction to the PC plus 1. This is PC plus 1, right? So basically, you need to provide the data paths to data connections, muxes, as you can see, and adders to actually calculate the address in the data path. And our data path is now becoming more complicated, as you can see. Before, I didn't show you this internal picture, but now we have an internal picture for the data path to do the address calculation over here. And again, we didn't talk about every single possible path over here. All of the other instructions actually, some other instructions actually exercise these paths, as we will discuss later on. Okay, let's take a look at MIPS. In MIPS, LW, load word and store word, use base plus offset mode, as we discussed earlier, actually. This is also called base addressing mode. High-level code looks like this, as we have seen before. And you've also seen this before in the previous lecture, right? Basically, MIPS assembly looks like this. Base register is S0, and basically we address the 8th byte after the base register to get the word over there. Remember, words, everything is byte addressable, and a word is 4 bytes. That's why we multiply the index with 4 over here to figure out what is offset. And basically, this is the semantics of the instruction. Well, this is store word, sorry, this is not load word. We've seen load word in the past, but essentially it's the same. The calculation of the address is the same. Whether you're writing into the register or writing to the memory is what's different between load word and store word. And this is the, again, instruction encoding. Again, immediate here is the 16-bit offset, which is sign extend to 32 bits. So let's take a look at an example program in MIPS and LC3, which is going to be very, very similar, actually. The high-level code looks like this. You basically access an array element that's array A0 over here, add to it B and subtract it from it 5, and then store the result into array B's 0th element. Okay, so MIPS registers we're going to allocate as follows, as like this. You can follow it in the picture over here. Okay, MIPS assembly basically will look like this. First, we're going to load with base plus offset addressing the A0 into T0. And then we're going to do the addition, T0 and B over here. And then we're going to do the subtraction, if you will, or add immediate -5. And then we're going to store the resulting value T2 into base plus offset addressing mode, using the base plus offset addressing mode to the first element of B0. Okay, LC3 assembly looks very similar, basically. It's not much difference, as you can see over here, except for the notation, if you will. There's not much difference. I'm not going to go through this, but load word is LDR, add is add, except LC3 doesn't have an add I. It basically uses the same add operation. But in an assembly mnemonic, you can actually change that to add I also. And SW turns into STR. Registers are also, of course, different. But again, offset addressing mode is very fundamental to many, many ISAs, as you can see over here. Let's talk about immediate addressing mode as well. This is going to be how we construct values. This is called load effective address. It's a bit unfortunate naming, let's say, but you will see what it does soon. Basically, it looks similar to some other operations, but the opcode is different. And we have a destination register. And essentially, this is what it does. It doesn't access memory. It basically loads the destination register with the following value: PC, incremented PC as usual, plus sign extended offset, 9-bit offset from the instruction, bottom 9 bits of the instruction. So basically, difference from the PC relative addressing mode is we don't access memory over here. So LEA actually constructs an address and loads it into a register, but it doesn't access memory. So the purpose could be, for example, address manipulation over here. You may want to manipulate addresses so that you can decide where you want to access in memory later on, right? So that's one purpose. Another purpose could be constructing some value that you may want to use later on. Essentially, we do not access memory in the fetch operand stage over here. We just construct an address and place it into the destination register. That's why it's called load effective address. And you may see later programs that we use. So this is the assembly and machine code. I'm going to go through this relatively quickly again. And this is what it looks like. There's no memory access involved, as you can see. You take the incremented PC, add to it the sign extended 9-bit immediate. After sign extension, it becomes 16. And then the result goes into the destination register. Okay, now this is this is in the LC3 data path somewhere that you can find. Actually, it's here, right? Okay, wait, let me actually go back over here. So this sign extended 8 bits. So it basically goes through here and you write into the destination register. So it's an interesting path over here. It's actually interesting to figure out where it goes through. So you have the sign extended 9 bits. You have to select that one, add to it the PC plus 1, which comes from essentially here, and then take the value through the MAR mux, gate MAR mux, and put it into the register file. So that's the data path you need to follow to actually write the data into the register file. So you'll become an expert in following this later on. So I'm doing this very quickly so that I can give you an idea of, you have to have the data path for every single instruction, but don't worry about it if you're not fully following it. You're going to do a lot of exercises related to this. Let me also tell you about the immediate addressing mode in MIPS. There in MIPS, load upper immediate, an instruction loads a 16-bit immediate into the upper half of a register and sets the lower half to 0. This is how you can construct a value that's larger than some immediate value that you can encode in an add instruction, for example. So it is used to assign a 32-bit constants to a register. Let's take a look. So let's assume that your high-level code is like this. I want to generate this number, 32 bits, and assign it to a variable. Mips assembly looks like this. Essentially, you have this load upper immediate instruction, which loads the upper 16 bits of S0 with 6D5E, which is the top 16 bits of this value. And then you can OR immediate S0 such that with a 16-bit value, such that you can set the bottom 16 bits. Hopefully that makes sense. So basically, you construct the 32-bit value by loading upper immediate, upper 16 bits using the LUI instruction. And then you set the bottom 16 bits using the OR instruction, or immediate instruction. Okay, so this is an addressing example in LC3. I'm not going to go into detail. Actually, I'm not going to go at all here. This is for your benefit. And I would recommend you actually go through this so that you really understand how things go. I'm just going to give you an example of how you should go about looking into it. Essentially, you're given this machine code, let's say. Somebody may ask, what is the final value of R3, right? In fact, they may not even give this part over here on the right over here clearly. This is actually for our help. So basically, you're given this machine code, and the question may be, what is the final value of R3? And a lot of people actually do this in their lives when they're doing security analysis, for example. They may reverse engineer code like this. So the first step is really understanding what your opcodes are, essentially decoding instructions using the instructions that architecture manual, and then understanding what the values are. These are immediate values. And then understanding what the registers are. Usually these are registers over here. Essentially, you decode your instructions and execute them. Basically, as a human, you do what the computer does. And once you do that, you will figure out that the final value of R3 is 5. If you get something else, let me know. But take a look and do it on your own so that you can actually study. We could actually put it as a homework question also. I don't remember if we actually used it as a homework question this time, or if you will use it as a homework question this time, but it's a good idea to use it as a homework question. And this will actually enable you to really understand how the instructions operate. Okay, so this is a really good time to take a break at this point before I move on to control flow instructions. We have covered a lot, but we have covered something that's really not important, which is the last part of ISA that I would like to cover, the control flow instructions. So let's take a break over here until 15:25, and then we will start with control flow, and hopefully we'll cover as much as possible in assembly programming. So I will see you after the break. Okay, let's continue the lecture. So remember, we talked about control operate instructions, and now we're going to talk about control flow instructions. And this is the program to study on your own and reverse engineer. Hopefully, it'll be fun. And reverse engineering is actually a great way of learning how things actually operate or behave. Okay, so let's talk about control flow. Remember that these instructions allow a program to execute a sequence out of the
sequential order. And these consist of conditional branches and unconditional jumps. So control flow could be unconditionally changed or conditionally changed, depending on some condition. Conditional branches are used to make decisions, for example, the if-else statement, or to enable loops. In LC3, we use condition codes, as we will describe in a little bit. There are 3 condition codes, positive, negative, or 0. And depending on the condition code you're testing, the conditional branch is taken or not if the condition code is set, if the tested condition code is set. Jumps, on the other end, are used to implement loops and function calls. You can have basically have the JMP in LC3 and J in MIPS, which we have seen at the end of yesterday's lecture. Now, let me introduce condition codes to describe conditional branches in LC3. So condition codes, for example, don't exist in MIPS. We're going to see a different way of handling, but they do exist in x86, for example. x86 ISA has condition codes, and LC3 also has condition codes. So they're one way of really implementing a conditional branching in an ISA. Different ISAs tackle it differently. So it's important that you learn both ways of doing it, I think. So for example, in LC3, each time one general purpose register, R0 through R7, is written, 3 single bit registers are updated based on the value that's written to the general purpose register. So each of those condition codes are set to either 1 or cleared. And they're basically 3 condition codes, N, Z, P. And if the value written to the register is negative, N is set, Z and P are cleared. If the written value is 0, if you're writing a 0 to the destination register, Z is set, N and P are cleared. And if the written value is positive, P is set and N and Z are cleared. So hopefully it's obvious. Basically, it specifies, these condition codes specify what was the value that was written to the destination register with the previous instruction that wrote to it. Is it negative? Is it 0? Or is it positive? And now you can take a decision, take a branching decision based on that, right? And x86 and Spark are examples of ISAs that use condition codes. And MIPS clearly does not use condition codes, right? Okay, so conditional branches in L3, let's take a look at one example. So BRZ is branch if 0. It tests the Z condition code, basically. And if the Z condition code is set, it basically takes the program counter to a value. So the question is, how do you determine that program counter value? So this is the opcode. These are 3 bits that are supposed to be set depending on which condition code you're testing. If it's BRZ, you set Z bit to 1, and N and P are zeros over here because you're supposed to test the Z condition code. And PC offset 9 should specify the target address of the branch. What should the program counter be changed to if this branch is taken? Okay, so basically these NZP bits in the instruction encoding specify which condition code is tested. It could be multiple of them. You could actually set all of them, as we will discuss later on. These are instruction bits to identify condition codes to be tested, small NZP. Large NZP are actually the condition codes in the machine, and essentially the values of the corresponding condition codes. So PC offset 9 is very similar to what we have seen before. This is the 9-bit offset, immediate or constant value. Now, let's take a look at the specification of the instruction over here. If the N condition code is set, and if you're testing the N condition code and the N condition code is set, or if you're testing the P condition and the P condition code is set, or if we're testing the Z condition and the Z condition code is set, then PC should get PC current value, incremented value, plus sign extended 9-bit offset. So basically, this is how you calculate the target address. PC incremented already, plus sign extended 9-bit offset, right? That's the target address of the branch. And you change the program counter to the target address only if the condition code you're testing is set to 1, which is true, right? And you could be testing any of the 3 condition codes. So this is the most general form. This particular branch is testing the Z condition code. So the Z is set to 1, and it will change the PC to this target value only if the Z condition code is set. It doesn't care whether any condition code is set or not, because it's really testing the 0 value, whether that's the previous value that was written to the register was 0. So there are many, many variations of it, as you can see. In fact, there are 9 variations. You could have branch N, Z, P. Okay, you can basically test multiple different combinations of test condition codes, which makes it really powerful. So BRNZP is actually, think about what you're doing over here. You're testing all of the condition codes.
which means that it's unconditional, right? Because the previous value that's written to a register cannot be, must have set at least one of the condition codes. Well, in fact, exactly one of the condition codes, I should say, not at least, exactly one of the condition codes. And if we're testing all of them, this is really an unconditional branch at this point. Okay, we'll see that again later. So BRZ looks like this, basically. You're jumping, this is an assembly code. This is the offset, 9-bit offset over here that's provided. And this is how it works, basically. A Z-bit is set over here. So essentially, we're testing the Z-bit condition, Z condition code. If Z condition code is set, then this will evaluate to a yes, meaning that yes is controlling the PC, whether PC is going to be loaded, right? And then what PC is going to be loaded with is going to be PC, incremented PC, plus sign extended 9-bit offset, which is this one over here. And then that will be put into the program counter. And this yes means that you're going to update the program counter, meaning enable the writing of the program counter with the correct value. As we will see later, there's some complication over here, which I'm not describing right now. But basically, yes means that PC should be updated with this particular value over here, as opposed to PC plus 1, let's say. Okay, so there are two cases over here that are kind of interesting. What if the bits in the instruction are all 1? N and Z and P are all equal to 1, meaning you're testing all of the condition codes, meaning you have branch and ZP. This means that you're unconditionally branching because at any given time in the machine, exactly one of these condition codes is set, because whenever you write to a register, these condition codes is set, and the last write to the register must produce a value that's either negative, 0, or positive. There's no other way around it, basically. Okay, and what if NZP are all 0, meaning the instruction is not testing any of those? That means that this instruction is a no op, right? No operation. You're not testing anything, which means that you actually have a BR no op, if you will. The branch is always going to go to the next instruction, basically. Okay, so there are two corner cases over here. Okay, in MIPS, things are different. Basically, you don't have the notion of condition codes. Remember, the condition codes exist. x86 actually has a different set of condition codes, which I'm not going to talk about. There are more than, I think there are 5+ condition codes. There, you can, for example, branch on the carry flag or overflow flag. There are different flags. They call it flags in x86, but it's essentially the same thing as condition codes. In this case, we have 3 condition codes only in LC3 to make things simple. MIPS doesn't have that, basically. MIPS said, we don't want to have condition codes. They're actually, this is a trade-off in the ISA also, which we're not going to cover, why you don't want to have condition codes. They basically said, we're going to do branching using this sort of instructions. So this is an instruction, branch if equal. So it basically has 2 register operands and a 1 offset operand. And it looks like this. The opcode is 4, as you can see. Source registers are RS and RT. Offset is the immediate or constant value. So basically, branch equal checks if the value in RS is equal to value in RT. And if that's the case, then PC gets the target address, where the target address is computed as PC plus sign extended offset, 16-bit offset, multiplied by 4. So you can see that you can actually jump to a much larger space in memory over here in the program. And you multiply it by 4 because clearly this is a byte offset, and we're doing basically you specify the offset in terms of bytes, as you can see, because this is byte addressable. So it's very similar to target address calculation, is very similar to what we kind of saw over here. It's PC relative addressing, right? Basically, we had the PC offset plus PC over here. We have the same thing over here, essentially, PC plus sign extended offset. But the way we determine whether we branch, whether we take the target address, whether we put the target address into the program counter is different. We don't check the condition codes here. We check whether 2 registers are equal. Clearly, this is more complicated, right? You're basically comparing 2 registers in this case. So Mips Assembly looks like this, but LC3 assembly looks like this. Basically, if you want to accomplish the same thing that MIPS does, LC3 is more complicated, meaning it requires more instructions, right? Well, what do you do over here? Basically, you check whether S0 and S1 are equal. The instruction does it for you. Here, you have to do it yourself to set the condition code. Basically, you need to subtract R0 from R1. And if they're equal, the result will be 0. And you take the branch if it's 0. Basically, you jump to offset if the condition code is 0, really, after this operation, right? Whereas the instruction does all of that for you inside MIPS. So this is one place where MIPS is more complicated as an instruction set compared to LC3. And as a result, it's closer to the higher level language. And as a result, you can encode this operation with a single instruction as opposed to four instructions in LC3 over here, right? So this is another example of the trade-off used in the instruction set. The same functionality requires more instructions in LC3, but the control logic requires more complexity in MIPS in this case. So hardware is more complex here, whereas software is more complex here, right? Again, same semantic gap that we discussed earlier. So this is almost the end of lecture 10A, except I put a few more slides before we go to assembly programming, which is 10B. So essentially, we've covered all of this so far. We really covered how a computer executes instructions and what the instruction set architecture looks like. Clearly, we didn't cover every single instruction. We covered the instruction formats, different addressing modes. Now you should be able to write programs, as we will see next. But I will also mention what we have not learned, which may be actually useful for some of you, because some of you actually have more advanced questions, like, for example, why is Apple M1 executing x86 code better than x86? There are multiple possible answers to this, of course, but one of the things they could be doing really well is they could be translating the x86 ISA instruction set architecture into their own internal architecture, internal instruction set. And that's one technique used to translate one language to another language internally very quickly, so that they can actually execute it much more efficiently, potentially. And that is an old trick that was used by other architectures in the past. We don't cover that sort of issues, but if you're really interested, you can actually look at some of the lectures that I have delivered in the past. We don't cover it in this class because it's an introductory class, but if you're really interested in ISAs and hardware-software interface, we actually cover a lot more depth in a class that's later in the sequence. And you can take a look at that. But let me quickly talk about the historical perspective. There have been many different ISAs over the decades. x86 has been very powerful. Some of them are dead now, like PDP, Program Data Processor. Interesting ISA, it's dead. VAX is dead. IBM 360 is dead. CDC 6600 is dead. Some SIMD ISAs still exist. That's not necessarily these ones. VLIW, very long instruction word. We're going to cover actually SIMD and VLIW. These can actually do multiple operations, specify multiple operations with a single instruction. For example, single instruction, multiple data, for example, or very long instruction word. We're going to see that. Power, PC, and Power still exist. They're actually interesting ISAs. And they're also more reduced instruction set computing ISAs like Alpha, MIPS, Spark, ARM, RISC-V. And clearly, some of them exist and some of them don't exist. Don't exist mean they're not developed further as machines that implement them, right? And clearly, there are differences between them, like how instructions are specified and what they do, how complex are the instructions. There are many, many differences, which we're not going to cover. But let me quickly end up with this important thing that we covered briefly. But this is actually a very fundamental place where you place the ISA, whether the instructions are complex and the data types are complex or simple, right? Complex instruction, an instruction does a lot of work, meaning many operations, potentially with higher level constructs, like insert into a doubly linked list, compute the fast Fourier transform, string copy, which exists in x86, for example, or matrix multiplication. Complete matrix multiplication is another example. Whereas simple instruction is an instruction does little work. Essentially, you're thinking of an instruction as a very simple primitive using which you build complex operations on top of them. Where here, you're thinking of an instruction as oh, I have a high-level function. That could be an instruction for me. I don't need to go and build it out of very primitive operations. So semantic level of the instruction is very high over here, whereas the semantic level of the instruction is very low over here. Meaning that the instruction is very closer to the hardware and the control signals, whereas here, the instruction is farther away from the hardware. So for example, here we have add, not, XOR. Even multiply didn't exist, for example, in early MIPS architecture. And then they added multiply because they decided, okay, that's a bad idea not to have multiply in our ISA. It's a bad idea not to have floating point in our ISA. It's a bad idea not to have byte operations in our ISA, because these are things that are very heavily used in programming languages. So clearly, this is there are advantages and disadvantages to complex instructions. And complex instructions enable denser encoding, clearly. Your program can be much smaller, basically. As a result, your memory utilization will be less, higher, for example, your memory waste would be less, let's say. You save off-chip bandwidth, you get better cache hit rate, as we will see later on. Don't worry about these right now if you don't understand what they are. But you get better packing of instructions in a given amount of space, because your instructions are very powerful, right? And your compiler is also simpler because you don't need to optimize very small primitives as much. Whereas disadvantage of complex instructions also exist. Now you have larger chunks of work. Compiler has less opportunity to optimize, limited fine-grained optimizations it can do. Of course, you could argue that you could have both types of instructions and enable compiler. Yes, that's true, but then your ISA becomes even more complex. And the big disadvantage of complex instructions, you get more complex hardware. Basically, you need to translate from a high level to control signals, and optimization now needs to be done by the hardware as well. So this translation can be done in hardware, can be done in software. And I think the question of like, how does Apple execute x86 code is a very interesting question. I don't think Apple reveals that sort of stuff, but they could be doing translation in hardware. They could be doing translation in software. I don't know, but I believe they are doing some sort of translation to their own internal instruction set architecture. So another example trade-off, number of registers. This is also important, I think. Clearly, if you have more registers, there are benefits to it. But if you have more registers, you need to have more bits to encode the register address. But you can have more values kept in fast storage. But you need to implement a larger register file if you have more registers, right? Size, access time, power consumption of the register file increases. Large number of registers actually enables better register allocation and optimizations by the compiler or the programmer. Fewer saves and restores into memory, as we will see in the next lecture, quick lecture. But it leads to a larger instruction size and a larger register file size as well. So clearly, all of these things that you do in the hardware-software interface lead to trade-offs. And usually the trade-off is between the software complexity or ease versus the hardware complexity. And that's what we're dealing with in general. And sometimes the trade-off spans both, actually. For example, larger instruction size affects both, right? Both the hardware may become more complex and the software may become more complex because you have a larger instruction size and you need to waste more memory for that reason, but you may get some benefits. Okay, so there's a lot more to cover on ISAs, and I would recommend you take if you're really interested, you take a look at these old lectures that we have from CMU if you're interested. And these are the links to the lectures directly from the slide. Okay, that brings me to the end of Instruction Set Architectures 2 lecture.